Welcome to this video on the electric field part 6. In this video I'm going to look at the solution to the problem that I left you with, or the challenge I left you with at the end of the last video, and then also take a look at how I would draw the field map for this specific configuration. So just to recall, I have a configuration where I have three charges that are all the same value Q, and they are spaced out at the points of this equilateral triangle. Now at the centroid right there in the middle, that is a place that's equidistant from each of these sides, right? That was the place that I asked you to figure out, is it possible for the electric field at the centroid to actually be equal to 0? Is that a possibility? And that's what we're going to take a look at. So I've got an image down here that just has some of the layout of an equilateral triangle, just to kind of help with some people who like to visualize it this way. Now what's most important to remember is that we're looking at what is the direction of the field at that point, that centroid point. So from charge 2, the electric field is pointing up to the right, so that would be E2, and from charge 3, the electric field at that blue point is pointing up to the left, about like that. And then due to charge 1, the electric field is pointing straight down like so. Now I'd already shown that in the x dimension, right, the horizontal dimension, that E2 in the x, which I'm calling positive, minus E3 in the x, which I'm calling negative, it was kind of clear to see that those two canceled out. And then we were looking at, really the question was, what about the y dimension? Can that cancel out too? And in fact it does. So the most important to think of here is this just as vector analysis, right? We already looked at this version here, E2 in the x, we looked at this, which was E3 in the x, and now we're going to focus on the y here and the y here. Well, based on some fairly straightforward geometry, we have a 30-degree angle here with the horizontal. And so what we can see is that E2 and E3 lie more in the horizontal dimension than they do vertically. So that must mean that their vertical components, right, they have two vertical components pointing both up. Those two are smaller than E2 itself or E3 itself, right? Because that's one of the legs of the right triangle that would be formed to make this vector. And so I can see here that the value of E1 will be negative, so E1, and it's in the y, it's all in the y, and the values of E2 in the x and E3 in the x must therefore be add up to E1 in the x. And you can figure that out by looking at the dimensions here. And if I do that, I can see that that will actually sum to 0. Finally, when you're putting E in the x, or E net in the x, plus E y, or E net y, I'm going to square both terms and take the square root, and that would give me the net electric field. That was the combination of both, which in this case at the centroid would be 0. Now obviously the centroid's not always going to be 0 because it depends, right? If I change this to 2q, it would push this down, the 0 point down closer to these two. I could have changed, these to different values. One of these could be a negative sign and so on and so forth. So you can figure out, and you always just isolate the point you're looking at, draw in the one electric field vector that is at that point due to each of the charges, and then you can sum them up using vector addition. So next what I want to do is I just want to show you what the field map itself would look like for this electric field, and that's not a very good drawing, so let me go ahead and fix that. So this is approximately the same drawing that I have up here. And remember, the field lines point away from positive charges, and so we probably could start by just drawing these ones out here on the ends, any that are pointing outwards, because we know that the net field is going to cancel out in the middle. So what's essentially going to happen is I'm going to have something that kind of does this weird curve, something like this, and it points out all away from the middle. And obviously these would be kind of super curved over here. And so we have something like this where there's a big patch open in the middle. Now this isn't a very good drawing, and you might be wondering, well, how do you actually draw the real field map? Because this looks like crap, basically. And so the question is, how do you actually construct a field map? Because we know that if we have this configuration, we have an idea that, okay, the arrows always point away from positive. They're strongest in the most dense places, weakest in the least dense places. We have all those basics down, but how do we actually construct the field map more predictably so that it's repeatable and that it would look the same every time? Well, that's what we're going to take a look at in the next video. And what I am going to show you is the method and the process by which we actually understand how field maps are constructed. So they're not these random things where I just kind of draw lines that make reasonable, rational sense, but there's actually a series of very mathematical steps that we can use to draw this particular field map. So when we come back in the next video, we'll check that out. Meanwhile, you can do some practice on different configurations and figuring out the net electric field.